Section 3.3, real zeros of polynomials. Everything we're doing in this section is pretty much related to finding the roots or zeros, solutions, x-intercepts of a polynomial or a polynomial function. And everything we've done up till this point, they've given us a zero or it's been easily factorable. But what if it's not? What if it's not easily factorable? What if they don't give us any zeros? The rational zeros theorem states that the only possibilities for a rational zero for a polynomial are factors of the back over factors of the front. By back, I mean the constant number, the last number in the polynomial. And for front, we're talking about the leading coefficient. So it's just the factors of those, and it's all of the possibilities. So let's look at an example. So for the polynomial 2x to the third plus x squared minus 13x plus 6, this is not factorable by any easy means that we know. It's not factorable by grouping or anything like that. So let's go ahead and look at factors of the back, 6 over factors of the front, 2. And it's all of the factors. So factors are things that can multiply to equal that number, or you could say that they are divisors that go evenly into the number. So for 6, we could do 1, 2, 3, and 6 over factors of 2, which would just be 1 and 2. So then I think it's useful to actually write out all the combinations. So you could do 1 over 1, which is 1, or 1 over 2, 1/2, or 2 over 1, which is 2, or 2 over 2, which is 1, so we don't need to write it again, we already have it, or 3 over 1, or 3 over 2, or 6 over 1, or 6 over 2, which would be 3, and we already wrote that, so we don't need to write that again. So these are all of the possibilities for rational zeros, rational roots, except they're all plus or minus. It could be the positive or negative for each of these. So there's really 2, 4, 6, 8, 10, there's really 12 options here. So to figure out which ones actually are roots or zeros, you can either plug them in and see if you get 0, or you can do synthetic division. So let's go ahead and do synthetic division. 2, 1, negative 13, and 6. Let's just start with 1, because 1's the easiest in my opinion. Bring down the 2, times 1 is 2, add 3, times 1 is 3, add negative 10, times 1 is negative 10. That's not 0. So 1 is not a 0 of the function. So let's try it again. 2, 1, negative 13, 6. And this time let's try, I don't want to try 1/2 yet, that's more difficult than we need to. Let's try 2. So bring down the 2, times 2 is 4, add and we get 5, times 2 is 10, add we get negative 3, times 2 is negative 6, add we get 0. So yes, 2 is a 0 of the function. And that means that x minus 2 is a factor. And when we factor out the x minus 2, we're left with our answer to the synthetic division, which is 2x squared plus 5x minus 3. Then from there, since this is a trinomial, we can actually factor this using our old methods. So my preferred way is to multiply the 2 to the back to get negative 6. Then factor this, so multiply be negative 6 and add to be 5. That's going to be positive 6 and a negative 1. But we need to divide by that 2. So this would be x plus 3, and bottoms up 2x minus 1. So this is it completely factored. P of x in factored form right here. So checking all of those possibilities can be a lot, so there's some tricks to help narrow it down. Descartes came up with the observation that the number of positive roots is equal to the number of sign changes in the polynomial, and the number of negative roots is equal to the number of sign changes in p of negative x. And it actually could be fewer than this, but this is the maximum number. And actually when it's fewer, it can only be an even number fewer. So, or it could be 2 or 4, 6, fewer than that answer. So by sign changes, we're actually looking in the polynomial. It's positive, positive, positive. Finally, when it goes to a negative, that's a sign change. So there's, for positive, there's only one sign change here. It's all positive, and then it switches to negative and stays negative. So there's only one positive root. For the negative roots, we need to find p of negative x. So p of negative x, when you plug in a negative x, since it's to the 6, it'll be the same thing. It's just 3x to the 6th. When we plug in a negative here, since it's an odd power, that'll change the sign to a negative. Odd power will change this again to a negative. An odd power will change that to a positive. And then just a constant will be negative 3. So now, for the negatives, it's positive and switches to negative, that's 1. It stays negative, still 1. Changes to positive, so now it's 2, and then back to negative. So there's 3 sign changes. So there's 3 possible negative roots, 1 possible positive root. So that would just mean that if we found that one positive root, we could stop checking the positives and only check the negatives from there on out. So there's another trick that when you're doing synthetic division, we're dividing the polynomial by something, we'll call it b. If your answer row, which includes the remainder, has no negatives in it, they're all positives or zeros, okay, that means there's no roots that are larger than b. So there's no need to check anything bigger than b if everything is positive or 0 in the answer. Similarly, we could say if the answer row alternates signs, then there's no roots smaller than b. And for this, we can count 0 as either positive or negative. So, for example, positive, 0, positive, that would count as alternating. Or negative, 0, negative, we can count 0 as a positive if we need to, and that would count as alternating as well. So for this example, we want to show that all the real zeros of the polynomial x to the 4th minus 3x squared plus 2x minus 5 are between -3 and 2. So that means that we need to do synthetic division on the polynomial. So 1 and then a 0 for the x to the third. -3, 2, -5. And let's start with the -3. So let's do our synthetic division. Bring down the 1, multiply -3, add, multiply, you get 9, add, you get 6, multiply for -18, add, you get -16, multiply, you get +48, add, you get 43. So the signs alternate, positive, negative, positive, negative, positive, which means that there's nothing smaller than -3. Then we'll do it again for 2. So bring down the 1, multiply to get 2, add 2, multiply 4, add, you get 1, multiply 2, add, you get 4, multiply, you get 8, add, you get 3. They're all positive all the way through, so there's nothing larger, no roots larger than 2. And that's all that they wanted to show. Nothing smaller than -3, nothing larger than 2.